Well, it's kind of a good news, bad news thing following Whit Gibbons. The good news, he provides an excellent segue for some of the things I wanted to talk about. The bad news is anything I say is going to look pretty meager in comparison. So you have to keep that in mind. But basically, what I want to talk about is actually some of, I guess, what I call the beginning of some long-term monitoring efforts on our part on some commercial timberlands. To give you a little perspective where this is, it's as a matter of fact, right immediately in this surrounding area here in north coastal California. You see all that in green is portions of the ownership. About half of it, the western half, is primarily redwood lands. The eastern portion is Douglas fir and hardwoods, approximately 450,000 acres. Now the work that we're doing and the monitoring we're talking about is all supported under a habitat conservation plan. And my purpose here isn't to talk about habitat conservation plans, but I want to make a little plug for this, and that is Whit has just talked about the importance of long-term monitoring. Well, I don't know how you personally feel about habitat conservation plans, but one of the benefits of them is that they typically include a monitoring component, and most habitat conservation plans are 30 to 50 years. So we've been working on, we already have a spotted owl habitat conservation plan. We're now nearing completion on aquatic plan, which is a 50-year permit with a significant monitoring component. So we have the potential to monitor amphibians for the next 50 years, and the funding, of course, would be supported by the private timber company, but still there's that commitment for that kind of funding. So that is at least one of the major benefits of habitat conservation plans. The species, the primary species that are involved here are the focal species, are the 6 species, 4 salamanders, 2 headwater amphibians. Basically, these are cold water adapted species, the species that we consider to be the most sensitive to timber harvesting activities. And you saw Hart's talk earlier, and he mentioned the 2, the tailed frog and the torrent salamander, as being particularly sensitive to those kind of activities. Now this is the monitoring program. You have all the physical things that we're doing. I'm not going to talk about any of that today. I want to talk specifically about the headwaters amphibian portion of that, and to provide a little bit of what happened to the background of that? Well, I guess it didn't show up. Some of the disadvantages of attempting to quantify physical variables is that we may not necessarily know what's limiting or representative of stream health. We often don't know that the critical thresholds might be. And it's, the bottom line is a lot of these things are difficult, particularly in headwater streams. If you worked in there, quantifying physical variables tends to be quite difficult. And then the other reason, the other potential, thinking of it the other way around, is the advantage of the biological variables, is they have the potential to be more efficient, because if you measure one species and able to determine how they're responding, they're integrating a variety of things, physical variables, water temperature, water chemistry, physical variables such as sediment and so forth. So potentially you can get a lot more information for the same amount of work. And just an example of that, the difficulty of measuring physical variables in headwater streams. This is a headwater stream where there was a debris flow that was created by a culvert that plugged during a storm, and a massive slurry of water and rock and so forth came down this stream. And you see how it scoured it a number of meters up along the banks. Totally devastated the larval population of tailed frogs that were in the stream at that particular time. But the interesting thing, note this log here, take the same picture a year later, you can hardly tell anything has happened. And that's because these headwater streams tend to be transport reaches. The sediment moves through, and you generally, after the winter, it's hard to tell exactly what happened in there. So we're thinking that maybe this biological component is a better way of telling what's happening in these headwater streams. So some of the potential advantages, and you already, got a little spastic there, heard again from Hart, you heard that these things are sensitive to land management activities. They tend to be limited and don't move around a lot. They tend to stay in one place within the stream. So the bottom line is that the conditions for these, whether good or bad, are largely within our control, because it's mostly right there in that stream environment. And we potentially have the ability to monitor these, and that's basically what I'm going to be talking about today is our ability to in fact monitor these populations. Our basic design was this Baki design. Probably most of you heard that. The basic idea is you want to look at something before and after treatment, and you want to have treatment areas and controls. But this is a managed landscape, and the primary silviculture in this area is still clear cutting. So this is the type of landscape that we're looking at, and there's a number of problems right from the very beginning in doing this. We don't have the problem, the before and after problem, because we know where harvesting is going to occur. We can go out and monitor before the harvest. The key problem is coming up with controls. On our land base, we have a few small old growth patches, but they're typically 30, 40 acres and not nearly big enough to be of any value for looking at a headwater basin. We do have park lands adjacent. Here's some land here with the park adjacent to that, but trying to do work having controls in the park, there's a logistic problem. Then there's the other problem with the controls. Not only do you want the controls to be pristine or undisturbed, but they also have to be similar in other physical characteristics. And one of the key things, at least from our work that we've seen, is the nature of the underlying geology. This is a region, by this road cut you can see there's consolidated geology. Here's another road cut where there are no rocks. It's basically, it's unconsolidated. That makes a huge difference in the characteristics of the stream. Just some of the data, this is not what I'm here to talk about today, but you could see in consolidated for both tailed frogs and torrent salamanders, when we did a stratified random sampling of streams out there, a high proportion in these consolidated regions had tailed frogs and torrent salamanders. Unconsolidated, you see a very small proportion, so it has a huge impact. Just to show you an example of that, there's Laura standing right there. This is in the Headwaters Forest. We did some hike around the Headwaters Forest one day. And in general, the habitat for tailed frogs isn't very good in this pristine forest, and there was very little habitat for torrent salamanders. Again, it was because of the geology. In contrast, this is Turwer Creek up in Klamath. The wildfire burnt this back in 1988, and then it was salvage logged, so it had very heavy impacts. But despite that, it has good hard rock geology. Here's one of the streams in there where we've done some of our work. There's lots of tailed frogs and torrent salamanders, or I should say relatively high numbers in that region. So geology has such a huge impact. If you want controls, they have to have similar geology. You can't pick areas that have different geologies. At least that's my perspective. Now for the candidate species, Hart mentioned that the coastal giant salamander, I still call it Pacific giant salamander, did show impacts from harvesting. We haven't done much work with them primarily because we find them in pretty aggraded streams, and they don't appear to be particularly sensitive to land management activities. So our focus was on the torrent salamander, and this is in the adult phase here. Here's the larval phase where they have at least, in our region here, it looks like a 1 to 2 year larval period. So they're in the streams as aquatic obligates for at least a couple of years. They generally are in very small seeps. You can see this uppermost reaches of a stream, or in this case, it's an actually isolated stream. Isolated spring that pops out on the side of the hill where the habitat, exists. Now, in terms of the way they occur, they're in these small, generally, at least in our area, small, relatively isolated patches of habitat. There are quite a few of these, though, scattered across the landscape. And in general, our thoughts are that these things occur kind of like a metapopulation, with each one of these relatively isolated, and potentially, because they're small in size and have relatively small individuals. By the way, we don't really know what this number is. This is a guess, because generally you don't find more than maybe 20 animals at a given site. That they're relatively few in number, and therefore they ought to be pretty highly vulnerable to extinction. So our general premise in terms of the monitoring was to look at change in persistence of these subpopulations between the treatment and control. And then management actions would be based on whether there's a change in these extinction rates or if there's a decline in the average index of abundance. So our idea was also to get an idea of the average abundance in these particular sites. So ideally what you would have, and this isn't actually a monitoring site, but this is just an example Ideally, you would have come in here before any of the harvest. You would have determined what kind of levels of populations you have in this headwater seep here. And then somewhere over here, you would have another seep where there isn't going to be harvest, and that would be the setup. Now, in general, we've had difficulty finding that, particularly, like I said, finding the controls. And so we can't always find areas where there's not going to be any future harvest. So we often have to look at this in terms of relative amounts of harvest. The basic search is pretty straightforward. Right now we have 30 of these monitoring reaches. They're 10 to 30 meter fixed reaches. The animal search is 100% search with what I would call a limited rubble rousing. We do, as you see the rake there, we do pack rakes, but we don't use them very much. Generally, we do most of the work by hand to try to limit the amount of disturbance to the site. Well, it turns out it's not working. If you see both the treatment and control, both of these are in quotes, treatments in quotes because many of these sites haven't actually been treated yet. Controls in quotes because, again, the nature of these controls, and some of them aren't really the best designed. But what you see happening in all cases is these things are going in a downward trend. And our conclusion is that simply our searching every year out there working in that habitat is having too big of an impact, and we're basically destroying the habitat. So our attempt to monitor these sites is the long-term effect is to destroy the habitat, and you're not getting, obviously, the results you need. So I don't know if the conclusions, or I should say, are the adjustments to this. One of the things we're now implementing is we're going to increase the length of the reach so that we're not concentrating our impacts. We're going to have up to 100 meter variable length reaches. We're going to use a lighter touch and basically just move things that we can move without causing any general disturbance or movement to the site. We're going to probably do these searches every other year or every third year, and then we're going to focus on the persistence of the site, and we're no longer going to attempt to get a relative abundance. But in general, I think you can say, and I didn't put this up here, that this really isn't for monitoring. If we're trying to look at the impacts of timber harvesting, we're not going to get any answers for a long time. Now WIT considers, long time, 50 to 75 years probably, and we probably will get answers in that time frame, but the time frame we really need is a lot shorter than that. So let's look at another possible species. This is a tailed frog. I'm going to let Laura talk most about a lot of their life history characteristics, but they have the attribute that they have internal fertilization. By the way, she went out and caught a male and a female frog, and supposedly she's going to put on some entertainment this evening with those frogs at the banquet. But anyway, and they have this larval form that's adapted for being in freshwater streams and attaching to the substrate, feeding on diatoms. And the streams they're in are a little bit larger. They're generally downstream of where you'd find the torrent salamanders. They tend to overlap with the fish-bearing reaches, but they're still definitely headwater streams. Now, one of the advantages of these species is that they have at least a 1-year larval period, which means that the larvae are in the stream during the summer when bad things can happen, for example, too high of water temperatures, and they're also in the stream during the winter when bad things can happen because of sediment inputs. So that's one of the pluses to the larval populations, and that's why we tended to focus on the larvae. The adults are thought to be restricted largely to the riparian area, so again they fit the criteria of being largely restricted to that riparian zone in the stream, so that whatever's happening to their populations are largely under our control. So our objectives in this case was to compare change in larval populations between the treatment and controls. The management actions were required if there was a decrease in the treatment relative to the control streams or an overall downward trend in both treatment and controls. In this case, the ideal thing would be to have a number of streams to pick from, and so you could randomly select one. In fact, these are more headwater streams where you'd find torrent salamanders, so we generally don't find multiple streams where we can randomly select one, and we usually can only find one good stream to work with because they need to be somewhat larger. And then the controls, this is an aerial photograph of the landscape. You can see from the looks of that it's going to be difficult to find controls. In most cases, we could find a control stream in the same sub-basin. In some cases, we had to get a control stream that was in a different sub-basin. We do have set-asides associated with our spotted owl plan, and that's where we were able to get some of our controls. So the basic approach for doing this work, the stream layout, we walk up the stream and we lay it out and identify the different habitat reaches as either fast water or slow water. If you've done fisheries work, you know there's all kinds of breakdowns that you could put these things into. It becomes too complicated. We call it either fast water or slow water. Our sampling units are 1/3 of the fast water and 1/10 of the slow water units. And then so starting with the random start, we systematically select 30 of 3-meter belts. And depending on the size of the stream, the length of the habitat units, that means our monitoring reaches are generally 300 to 400 meters long. The actual animal search, the first thing you do is you put in a blocking net at the bottom end so these critters can't escape on you. Then you start moving the larger substrate out of there so that you can do a more effective search. And then we do a 4-pass search with a viewing device. This is actually Richard Wallace, my colleague who passed away a number of years ago, but anymore we mostly use a bucket device, but this is the same concept where you move up through the reach, multiple passes with removal. So you pull the animals out, make another pass. We do 4 searches. Unless the 4th search you catch more animals than you did in the previous search, then you have to extend 1 more searches. So we do these multiple passes on the individual reaches. When we started this work, we looked at like how many of these streams we need to do. We looked at this, a change of 25%, looking at the power versus the number of streams. And you can see that this really flattens out when you get between 15 and 20 streams. So that was our target in terms of how many streams. How much time?
1 minute.
Oh my gosh. So here's the results. In general, looking at all the sites have been relatively constant, although there's been some fluctuation. Treatment and controls, we haven't seen much of a change there. Now this was what you were supposed to be impressed with how much annual variation you're seeing, but after some of the stuff that Whit showed you, this probably doesn't look very impressive. But the real problem is there's a lot of annual variation. So our conclusions here is that we definitely can effectively estimate these larval populations, but the value of this is diminished by the high annual variation. So that led us to, well, maybe we should be looking at the adults, and that's a segue for Laura's talk. Thank you. Came pretty close.